All right, welcome to the Break It Talk. This is Exploring Novel Ways in Building Botnets by Daniel Mendy and Enno Ray.
Thanks for that, and good morning, everybody. I'm surprised to see so many people. I mean, it's the point of, say, 10 o'clock talk at Shmoocon Saturday might not be the optimal point for a talk, but still, many people here. Good morning. My name is Enno. That's okay. Well, I can't see it here, but yeah, we'll still work once I point to it. Do you see the point? I do not. However, Daniel, Enno, we are both from a German security company called ERNW. Some of you might know us from last year's talk on fuzzing layer 2 technologies. Before we dive into the talk, just a disclaimer. We do not use disclaimers, but this talk is a bit special as there might be technologies involved that could be used for the bad, and that's why we just want to say it's academic, it's a research talk. It's not about doing harm to the world in any way. This speaks for itself, so I won't comment on this. We like Shmoo, we like being here every year, and that's the main reason. That's one of the main reasons for this talk. The other one is, the talk is, say, a loose collection of technologies we stumbled across, protocols, and ways how to use them. That can be used. I mean, it's not in the strict sense about the inner workings of botnets, but it is about technologies that could be used or abused in the context of botnets. And so there is a double meaning. There's some demos in it, as we like to give demos, and hopefully they all work. And it's about, say, thinking or reflecting on protocols and their roles. The agenda is like this. We'll give some short introduction. What is a botnet and how does a botnet behave and how do the components interact? And then we have three major pieces. We are going to cover how some steps of an overall botnet, say topography or inner working, can be replaced or could be substituted with novel ways. Yeah, I mean, there will be some, we coded some stuff. All the code will be available after the talk, but I'll get back to this later. So what is a bot? Most of you will have an idea what a bot is. Say it's a piece of code running on some system performing actions, usually say some malicious actions, orchestrated by some centralized infrastructure, which is usually called, say, the bot masters. A bot's life cycle is typically composed of several steps. The first is, say, the initial affection of a box, which then becomes a bot. After that, now bot tries to contact some central entities to receive commands and to receive payloads. These payloads may be adapted for different purposes. These payloads may perform different actions. And this is exactly what the very purpose of a bot is about, performing malicious actions, which can be, say, performing DDoS attacks, which could be infection of other systems, which is called recruiting, which could be relaying of spam. This is declining as it's less and less needed to use bots for this, but which could be implementing various kinds of proxies for different purposes to hide, say, attackers or to hide malicious entities behind harmless, or in that case, no more harmless client computers. It could be clicking on paid advertisements. All sorts of, say, nasty stuff usually are performed by bots. The, say, traditional way of botnet communication was for a long time. This has changed a bit in the, say, last 1 to 2 years, but Before that, the usual way how bots communicated within that infrastructure, so the bots with the bot master or some intermediate layer was built or based on IRC communication. The main intent behind this was to avoid having the bot master. I can see it here, I can see it there. That is surprising, but okay. To avoid the bot master being detectable by, say, a fixed or given DNS name or IP address. Once it was detected, then it could be easily blocked. Exactly that should be avoided by that IRC communication. In the last, again, say 1 to 2 years, different botnets have undergone some changes, and there is more and more peer-to-peer technologies involved, like no more central, like client-server, but peer-to-peer communication combined with, say, very dynamic entity resolution structures. Which means there are boxes who try to register DNS names for a very short amount of time. Other boxes will resolve those DNS names. Those will be able to communicate within that time frame. So the stuff has moved to a more dynamic and peer-to-peer technology-based space. And there is a terminus which plays a major role there that's called fast flux. If you're interested in more detail what fast flux means, so we have some stuff here on the slides, but there is a German researcher, Thorsten Holz, which is working at Mannheim University, which in fact is 20 kilometers from ENW's place. So there is some, say, closeness, at least for the topology level. He has done a lot of research on fast flux. For us, it should be sufficient to think of fast flux like a very dynamic interaction infrastructure within bots, usually based on quickly changing DNS names. So the bot operators register DNS domains. Within that, they do so with stolen credit cards sometimes to avoid say traceability. And then within those registered DNS domains, in a very quick manner, the bot master or the bot master, say, registers and can be looked up by the bot clients, which in effect leads to a nearly untraceable infrastructure. And this will be the first part of our talk. We'll cover a similar mechanism which is not built on, say, abused DNS with stolen credit cards, but which is based on another protocol which is present in WinVista. Microsoft introduced, with WinVista, they introduced a whole bunch of new protocols and technologies. Those of you running WinVista or Server 2008 might have noticed there's all sorts of packets leaving the system of protocols most people haven't ever heard from, like LLMNR, Logic Link, multicast neighbor resolution, and there's a lot of IPv6 stuff going on which is enabled by default. And within that space there is one technology that is called PNRP, which is sometimes called the Bonjour killer. Like, it performs the same actions that Bonjour does in Mac space. That is, say, a distributed name resolution. And a dynamic name resolution, it requires IPv6. We'll cover the way how it works in a second. It's enabled by default in WinVista. It's somehow present, say, after you install XP/SP3. And the main intent is to have, say, an IPv6 replacement of DNS, which plays a major role in IPv6 anyway, but to have some technology which allows to dynamically register DNS names and to resolve them within a given space, which is in PNRP terminology called the cloud. There are several flavors of names, so-called secure and non-secure names. Those are somehow cryptography based. Okay, the secure ones. The unsecure ones are not. But suffice to say that PNRP is a quite, say, dynamic piece which does not mandate there are central servers present for name resolution. Somehow there have to be, say, entities that resolve, but those entities can be somehow built dynamically within those areas called clouds. The interesting point is to, say, propagate that technology. There are some PNRP servers in the internet, and given that Microsoft has a strong interest in, say, propagating IPv6 use with the Microsoft operating systems and the bunch of technologies built on that, those servers are operated by Microsoft themselves. So now put together what I told you about the way how fast flux works in botnets, like it's about dynamically and in a quick changing manner registering DNS names, and think about how PNRP works. And obviously there is some similarities in the sense that PNRP is about dynamically registering names which should be resolvable, which can change, and which can be found by other entities within some ecospace. So in fact, PNRP can easily be used for the same stuff that fastflux has been used before. We coded a piece like a small, say, bot name resolution component, which works in the way that all the bots within a given botnet have, a shared salt. The bot master uses PNRP to register a host name. This host name is composed, is a hash over that shared salt and the system time. So this host name changes every, say, 10 or 15 minutes. It could be 1 minute, could be 1 hour, whatever, say, the bot operators would like it to be. And this host name can easily calculated by all bots, by all drones, can be resolved by PNRP, and it disappears after that given timeout. So every, say, 1, 10, whatever you like, 30 minutes, a new name gets registered for the central entities. All the bots will be able to calculate the name and resolve it. And all this, operated on servers in the internet, which are, in fact, at the very moment, operated by Microsoft. It's not about, say, bashing Microsoft here. It's just they operate the servers that are present already. In code, it looks like this. I mean, the major part is the bottom of the slide. It's, as you can see, it's not too complicated code. It's not too many lines of code. It's quite easy to implement this in the .NET framework. I covered this one. The impact of this, just to put it into an image, is this: all the entities within a botnet will be able to use and abuse this infrastructure to implement some kind of, say, untraceable communication, as those names change. Again, they change quite quickly. We have prepared a demo here. Hopefully it works. We had it working before the talk, and we took a screenshot of that. We'll see. I mean, it's PNRP. We go through a double nut here, I think, in the Shmoocon net. We will see. But yeah, let's have a look. So this is one of those names, like compose a hash of a shared salt and the current system time. This does not look like it works, but again, we were clever enough to test it before the talk, and it worked, and to get a screenshot of that. Yeah, it's a bit, I mean, go through a double network address translation in a conference network. That's a screenshot, isn't it? Yeah. Okay. As you can see in the middle of the screen, the upper part of the screen shows the current active so-called clouds, and there is there is no, say, defined cloud of a given set of peers. There is a kind of internet cloud which is called the global one, and the name servers for the global one again are operated by Microsoft. There is a state active, which means we are not kind of alone there. The other state is alone, like we are in the cloud and nobody else is there, or we don't have contact to the cloud. And then you see in the middle part, there is a DNS record that I won't spell now, which ends on p0.pnrp.net, and those exactly is the domain kind of operated on those Microsoft servers. And so record 1 results, you get back some data. In the bottom part, you see an endpoint like 2001 :0. That is the IPv6 address. The other endpoint resolved to. And what is particularly interesting, I have not yet commented on this so far. PNRP allows not just to register a name, which happened, say 10 lines in the middle part of the screenshot show the resolution process based on some early registering, which can be, which is indicated by the cloud above. It's not only about registering names, but you can as well say register a 4K payload for various purposes. So this means the mechanism itself, PNRP, can even be used for distributing that payload. So think of like a DNS lookup where you do not get just a name, but you get up to 4K various data, binary data if you want. So this is indicated by the message that the guy who wrote this, Simon, put to the middle of the screen. So I go on here. Sorry it didn't work practically. I want to try once more. But you get the main pieces here. Yeah, it doesn't seem to. I don't think it just at the very. You might see that the name that is resolved has changed throughout the sequence of actions. So it is calculated based on time. Okay, I don't think it works, Daniel. Let's go on here and to not go over time. Yeah, we'll get back to that payload later on. So we have, obviously, we have some mechanism that can help us in the stage of a bot that is about registering names. Bots and botmaster find each other. So next step within a bot's life cycle is bot and botmaster should communicate to each other. Say, send status messages, send results back from a client, from a compromised client, like, okay, these are all the local passwords, or these are the passwords that I've sniffed. And to get, say, more, to get more payloads. Okay, we already covered this. This is what I had on the payload. I'll put a new battery in it for the second talk in the afternoon. So again, what we've covered so far is the technology for bots looking up botmaster. So next step would be bot communicating with the master, exchanging information, and in fact we have an internal project that we call ET, which is about say hiding communication and being able to implement communication from based on tunneling in standard protocols. The background is, last year we performed a pen test in a large enterprise environment, and they asked us, like, okay, we assume we can, some hosts of our landscape can get owned. We would like to show you, to show us if there are compromised hosts, if they can communicate to the outside world. And they have a pretty good security infrastructure with various layers of proxies and internal, external DNS and stuff. So we were forced to kind of code something which is able to communicate over DNS or HTTP, and which can again be used in a bot context. I suggest you go on here with the as you coded it. Do you want to advance the slides? Then. Oh, okay. You need the. Sorry, we only got one mic. Change this quickly.
So, okay, you can hear me? Okay, so I will tell something about the so-called Project ET. As Anna already said, it's just an environmental testing tool for looking for the hidden channels to get out of company networks and to phone home to get your bot, contact your bot master and get the payload instructions and stuff like that. So one of the final goals was that it should run on almost every Windows box, so I decided to write the whole source in C# and use the .NET Framework 2.0 because 2.0 is distributed with Windows Vista and almost every XP client got an .NET Framework 2.0. The software itself is not in a productive state yet, but maybe when I find some more time, I will finish the work. Okay, it's split up in two parts, one client component and one server component. So the client, first of all, has a user interface, which is not typical for a bot, but for our environmental testing tool, it should inform the user about the actual status and what tests are performed and so on.
I mean, that's what the client asked us for. Like, okay, if you can implement such a piece and bring it into our infrastructure, we would like to have, say, a status, like what actually can be done with it. That's why we have a GUI.
Okay, so, but I tried to use some common bot techniques, like hiding the program and using only high-frequently used system calls, like DNS resolution, which does not need special privileges. So here's a short screenshot. You will see the tool live in a few moments. The server itself implements pseudo DNS and HTTP server, which didn't bring all that functionality of a real DNS or HTTP server. It just is one end of the communication flow, and the server itself got a user interface too, so you can see which bots are connected to your server, which information they collected about the infected system, and you can send command to your bots. Okay, this is the first screenshot of the server component. You see some log file. This is the second one where you can see all the connected bots. But you will see this live in a few moments. Okay, let's have a look on the DNS channel. So, okay, tunneling through DNS is nothing new. Everyone tunnels everything through DNS, but it's still possible even in large company networks. So I will have a few words about the way it works. You need to cover both ways, the way out of the company network and the way back into the company network. So your way out first is just to resolve some host name. In this example, it's datbeef.test.enw.de, and your server component needs to be registered as the name server for this resolved domain name. Actually, your data you want to get out of that company network is encoded in your host name, which is datbeef in this case. And your server just acts like a real DNS server and will answer that request, which is Okay, this is one of the requests. And so that answer package of your, say, DNS server, your server component, is just the way back into the company network. The data is actually hidden in the IP address field of your DNS answer package. Okay, here's another screenshot. So, okay, that's very easy. Just get some DNS communication up and running and encode your data inside. But you have to look for some details. First of all, DNS is mainly transported via UDP. You don't own the infrastructure. You can't rely on the communication channel. So you have to get it managed that the packages arrive in the right order. You have to order the packages yourself. You have to retransmit lost packages and all that stuff. Within the DNS system, you have to disallow the caching mechanism. Because if you just resolve a name, the server can answer with whatever you want to. And so if there is some caching in the transport way, that will break up your communication flow. Okay, and the third point you will have to watch for is your request and answer packages should not get bigger than 512 bytes, because otherwise for transportation TCP will be used, and most company networks will not allow DNS requests over TCP. Okay, we just fiddled around a little bit with the amount of data transported via per request, and we found actually a limitation around 24 byte user data per request, which is not much. So think about, you got an MTU of 24 bytes, you won't get fast internet connection. Okay, the second part of this environmental testing tool was the HTTP channel. It works almost like the DNS one, but with one different. You don't request, or you don't resolve DNS names, but you request some URL. So this is the way out of the company network. You just encode your data inside the URL, and the way back in is the data encoded in the HTML body of your respond document. Okay, so this channel is not yet implemented because I had not enough time to do this now, but maybe I will implement it in the future. Okay, another point is if you want to use an HTTP proxy to communicate with the outside world, you first have to find that proxy. But remember, we're on Windows systems, and we got the whole .NET 2.0 framework ready for us just to help us find the proxy. So we could spawn an instance of an Internet Explorer object and read out just the locally configured proxy settings. If there is some authentication needed for that proxy, we can spawn an Internet Explorer object and maybe just reuse cache proxy authentication credentials. Even if there is some NTLM authentication mechanism, the only thing we need is a locally logged on user on the box, and then we can reuse that user credentials to bypass the NTLM proxy authentication. So this is nearly trivial with thanks to .NET. Okay. We will have to do some data encoding because both protocols, DNS and HTTP, are ASCII based. So I decided to encode the HTTP stuff with an base 64 encoding and the DNS stuff with an base 32 encoding. And that's just all for avoiding application layer inspection detection. Okay, so there are some problems left. One is that both protocols, DNS and HTTP, are user-initiated protocols. So you need to trigger and request even if you just want to receive data. That means you have to implement some kind of polling mechanism that looks out for data on your server side, which should be delivered to your client, and I implemented such a polling mechanism which receives first a randomly chosen sleeping interval by the server component, again to avoid detecting this. Okay, so we will have some conclusions and an outlook on this step. What's next is just to improve the implemented file transfer mechanism to transfer some binary data, to deploy bytecode. And after that, we can just think about all the evil botnet functions, like I said, dynamical bytecode distribution and execution. And with thanks to .NET, we got a beautiful botnet. So, okay, I will just give you a short look on ET in its current development state.
We will make all the code available after today.
Okay, so you see in this window, this is the server component. I will just start the DNS listener, and after that it binds to port 53 and listens for DNS requests. Now I use the ET client and just starts the DNS lookup. So it begins to poll a DNS name, and as you see in the status window on the left side, there are DNS messages arriving, and the client sleeps in a randomly given interval. So on the server side, I can have a look on all the connected clients, and they give me some data about when the last package from that client arrived, from which IP address it just connected. There is some internal state, and there could be some informations about the infected system given to the server component, like if you want to see which software is installed, which license keys are installed, and all the stuff like that. So, okay, as Enno said, we will just distribute the code after our talk.
Okay, then, so, yeah, I have to take
Thank
the mic. So far, what we have seen is how, say, existing protocols were abused for different purposes. I have no idea. Okay. For different purposes within the lifecycle of a bot. So far, we have a mechanism to look up, to perform the lookup, bot to bot master. We have a mechanism that enables communication between the bot and the bot master tunneled over DNS. That one is already working. HTTP is not yet implemented, but the DNS part works just fine. Then, as you might remember, in the overall life cycle of a bot, there is still some stuff left that is performing, say, malicious actions, which could be performing DDoS. And again, we found, say, like an example, how a given protocol, which is widely deployed, could be abused in that context. And this protocol, in fact, is SNMP. With SNMP, it will turn out you can perform, say, typical botnet functions, which in this case means performing DDoS, without even building a botnet infrastructure, without even, say, deploying of bots and compromising hosts and having a bot master infrastructure, but still be able to perform some distributed malicious actions. The next slide, so we covered this stuff of this section of the talk in a talk that we gave at the 2007 edition of in Hack in the Box in Dubai. So there is more on this in the slide set from that talk, which can be found on our website. The background is, most of you will know SNMP has some quite well-known vulnerabilities. There is some say, authentication or authorization mechanism based on so-called communities. Those have well-known defaults, that is public for the so-called read-only and the private for read-write. The protocol is based on UDP, which makes spoofing easy, and this will help us in what we are going to describe. And SNMP is still quite prevalent in the current internet and corporate network infrastructures, as most people don't really want to touch it, given the very nature of and the purpose of the protocol. There is, say, modern, where modern means the RFC was written 8 years ago or something. The modern variant, SNMP-v3, which addresses some of the weaknesses of the so-called community-based SNMP, but some of you might know last year there was a quite nasty bug found in major SNMP-v3 implementations, which essentially can be broken down to like with an SNMP-v3 you have cryptographic mechanisms to authenticate both parties, but by some implementation bug, the authenticator, the length of the authenticator could be indicated as 1 byte, so you were left with 56 possibilities for that authenticator. And the so-called secure replacement of old SNMP had large problems in itself. This is just for to give you an overview of the landscape. What does this mean for our potential bots, or what does it mean on an internet scale? In that, before the 2007 talk, we were part of a research project which at the time tried to get statistics on the SNMP deployment in the internet. And the data set that we disposed of was, say, scanning random pieces of the internet, and of all hosts that responded to a ping that we call a live host in that context. So we had about 240,000 live hosts randomly distributed in the internet. About 16,000 had SNMP with public, which is 1 of 15, and about 700 had SNMP with private, sitting in the internet, just looking. Which means 3 out of 1,000, which at the time we estimated the number of live hosts in the internet at 350 million. Currently it will be certainly more, but that means randomly distributed in that 350 million live nodes, there are about 1 million nodes sitting around which have SNMP enabled with a default community string of private. So everybody can kind of own them. SNMP private means you have control over the device. You can write to SNMP pieces. You can usually say reboot or put another image on the device. You can put another config on the box if it's a device or it's a host. You can do whatever you want. It's like it's kind of like having a root shell. It's not exactly because it's SNMP, but still you have full control over the box. So let's assume, and this is a valid assumption, there are lots of boxes sitting somewhere in the internet with SNMP enabled and SNMP private. We can say prove that assumption by, or to give you an idea what kind of boxes these are. We have, say, analyzed some of the results. In fact, we found 462 within those 700 pieces. I'm still used to. Okay, within that 700, there was a large number of network devices of extreme networks sitting around, and those are the devices. It's not small ones. I mean, it's crazy. It's crazy. You find those boxes sitting in the internet with SNMP private enabled. We had such stuff. We had, in one case, we found in one carrier network, so-called UBR 10,000, which is a universal broadband router, Cisco, serving up to 64,000 broadband subscribers. And that box had SNMP private enabled. The nice thing is that that box has built-in the image. It has to, depending on the country where it is sitting, I won't disclose that, it has to have legal interception capabilities, which can be enabled by SNMP. So we could have enabled the legal interception entities and put the so-called mediation device in there, like send us everything you would normally send to, say, FBI, send it to us. But that's not the majority of the boxes sitting around with SNMP. The majority, turns out, is SOHO devices like cable modems, DSL routers, all that stuff. And there are literally millions of those boxes sitting around with SNMP public enabled, but there is quite a few of them with SNMP private enabled as well, which is with the community thing public. Say Cyxel. Usually they use public for write and read access. So again, we have lots of boxes sitting in the internet just waiting to be accessed by SNMP in a fully controlled manner. What does this mean for, say, our botnet scenario? It means, remember that SNMP is UDP-based. We can easily perform amplification attacks like the once famous Smurf attack. The steps needed are usually, okay, we have to find devices that are SNMP writable. Remember, there is approximately 1 million of them just sitting there. Compile a list of those devices, write some long strings by SNMP into some, say, database places, ask for those strings with a certain SNMP command or SNMP operation, that is SNMP bulk walk. When asking for those bytes we previously wrote there, spoof the source address with the address of a victim. So this essentially can be broken down to one is able, with 60 bytes sent upstream, to get 1,500 bytes downstream, all on UDP, which means spoof the source address, and you have a ratio of 1 to 25, redirecting traffic into the direction of a victim without, without a bot or something. It's just plain SNMP and boxes sitting in the internet anyway. This is how it would look like in a graphical way. The attacker writes to those SNMP boxes sitting there. Usually we write 256 byte strings into various places, or we could do that. I mean, we'll give you a demo later on. Then we ask for the content we previously wrote there, and within that request, we spoof the source address. So it's the victim which gets back all the responses, and again, we are talking about a ratio of 1 to 25. So the attacker with a 2 megabit line can saturate 50 megabit line on the victim side. At the time Daniel wrote a tool for some SNMP attacks which can be found on our website, and this tool has the functionality we are talking about in it. At the time, there was no that hacker paragraph in Germany. It's still there. Nobody ever approached us, and it's a testing tool for performing security checks in your own infrastructure. That's I'm sure you are aware of that. Again, we have a demo here. We would like to turn off the camera for a second. The box we are attacking is a box that is owned by us. Thanks. Again, we have a case where a given protocol can somehow play a major role within an infrastructure that one would usually call a botnet. I'll summarize here. There is a number of protocols that can be used in a way they probably were not intended to be used. You already knew that about DNS. You might have known that about SNMP. We introduced that new IPv6-based protocol, PNRP. The motivation of our talk is to entertain you with some stuff, but to make you think about those ever-present infrastructure protocols and their roles, say, in modern networks. And we wanted to give you an idea how steps within traditional botnets can easily be performed maybe more efficiently with novel approaches. The background of our tools was not to implement botnets, but this was to say common denominator for all these technologies, and so the denominator for the title of our talk. All the code will be available at our download area, say at tomorrow sunrise. Any questions at this point? I think we managed to keep in time. Yeah. Do we have a mic runner or something? Other questions? I can repeat the questions once they come up.
What these types of tools over in Germany, do you guys have to worry about any of the new legislation over there?
Sorry?
It's my understanding that there's legislation over in Germany.
Yeah.
No hacking tools.
Yeah.
Do you guys have to worry about those types of issues?
There is the question was about the legislation in Germany about the distribution of tools that can be used for hacking. The answer will be in a twofold way. The first, a general perspective is that nobody has ever been convicted so far for this stuff. There's a large uncertainty to which cases this applies or does not, and we have you in the States, as far as I know, within your legal system, you have that approach of you need precedence cases, and once they are there, later, say, legislation or the later process is based on those precedence cases. We don't have any of those yet. The other point is, ERNW was founded in 2001. We have a number of federal agencies as customers. So we assume that we are regarded as, say, the good ones. So I'm relaxed as for this legislation. And I can tell you most other security researchers in Germany are as well. In the meantime, they do not care too much about this. Okay, any more questions? If there are, is there one? Ah, yes, Sergey.
Having read all of that Microsoft documentation that imitates Botnets, would you hypothesize that Microsoft has been actually informed by Botnets? Like maybe they thought something along the lines of, here is this really nice disruptive technology. Let's adopt it.
Yeah, the question is if what's the question? If Microsoft have been informed or if they have been aware?
Well, aware would be good. Informed would be even better because it would be an idea that was developed in, the Botnet community that turned out to be valuable enough.
Yeah, it is like that. Aware, I'm not sure. PNRP is, I think, a very good example of a technology that was invented for some use, and people describing, designing, inventing it, specifying it, were not reflecting on a potential abuse, which is legitimate not to do so. I think that's the background of the technology. As for information, I talked about this with somebody from Microsoft Security Response. They seemed not too interested, and it's a feature. It's not like we did not undergo the very formal process, but there was an informal one with some major person over there Yeah. Okay. We want to thank some guy that pushed us onto PNRP. He's called Dominic Byers, and a friend of us. We thank the Shmoocon staff for bringing us here, and we thank all you for listening to us. Thank you. Hi.
Hey, I'm Crispin of Shmoo.